In this video, I'm going to be going through the preliminary engineering studies. So this is the Year 11 HSC course, and we're going to be looking at Chapter 2, Question 19 and 20. These both are what I'd call lever questions, and what we're going to be doing is we're going to be finding an unknown force using moments. So in both these cases, we're taking moments about a fulcrum. So in this case, we're going to say that this wheel is the fulcrum and here the wheel is the fulcrum. Now, to do this, because we have effectively two unknowns, we need to use the sum of the moments about a point. So we have three formulas that we know to solve things. We know that this is a sigma. I'm going to write that out clearly. Sigma forces in the x direction equals 0. Sigma forces in the y direction equals 0, and then what we need to use to solve this one is sum of the moments from any spot equals 0. Now this is true for any system that's in equilibrium, so structures, wheelbarrows, whatever it is, that typically we're going to be finding things that are in equilibrium. So we're going to find at the exact moment where this is about to lift. We don't care about the moment once it's moving, we're looking at the exact moment where it's about to lift. So where it's still in equilibrium and just when that equilibrium is about to be disturbed. To understand the sum of the moments equals 0, what we need to know first is that a moment is equal to a force times a perpendicular distance. Now it's really important that we always consider perpendicular distances. If we don't use a perpendicular distance, we're going to have a bad time. So what we can do, there's a couple of methods we can solve. If there's only three forces, and we know that it's equilibrium, well, those forces will either be parallel or concurrent. So in this case, we can see that the forces that we know that the weight of this, so the mass times gravity of this wheelbarrow, is going to be vertical down. That's the definition of down, right? Things fall vertically towards the center of the earth. That's how we define down. We just don't use that terminology very often in regular speech. So here we have two forces, and we know those two forces are both parallel. If they're both parallel, that means that the remaining force must also be parallel because there's three forces. If there's three forces that are concurrent, we can use the three-force method. So that's a different way to solve these things. Now, in the situation where they're parallel, we have two ways that we can approach this. Here it's pretty easy because all the distances they've given us are perpendicular distances. That's a right angle. Here though, the distance they've given us, this force and this, they are not perpendicular. So this angle here is less than 90 degrees. And this angle here is greater than 90 degrees. So because of that, it means it's not perpendicular, which means we have to do one of two things. We can either break this force, we can turn that force into a vertical and horizontal component. Now when I say vertical and horizontal component, actually we're not going to take them into a vertical and horizontal component. Instead, what we're going to do is we're going to put them into an x and a y coordinate. So what we can do is we can create our own coordinate system. We call that x and that y. And once we have our own coordinate system, we can break this into the force. We can break this into force y and force x. Now, it's always important to remember that this force, when we're breaking things into components, that this force that we're breaking down has to be the hypotenuse. It means it has to be the biggest force. These two smaller forces have to add up to that bigger force. If we're taking a component where there are going to be two smaller forces. That's one way of solving it. And there's some real use in doing that, using that method. That has some benefits a lot of the time, because when we want to try and solve multiple parts, having everything already broken into components is a very useful way. So later on we're going to learn about more advanced moment questions. We're going to learn about trusses. And when we learn about finding reactions in truss systems and beams as well, Copeland says by default we should always break our forces into these components, into the x and y components. Usually horizontal and vertical components. In this case, they've asked us, and we're going to consider instead to go with we can go in the x and y coordinates. The other way that we can approach this is we can find instead, we're given a diagonal distance here, and what let me draw this in. We've been told this distance here. That distance here, we've been given that distance, but that is not a perpendicular distance. What we want is to find this perpendicular distance. So when we're given a diagonal distance, what we can do instead is we can use trigonometry to find a perpendicular distance. And if we can find that perpendicular distance, then that's another way to solve it. That's how I would solve this wheelbarrow question. I think that's a good way to solve it. But I'm going to go through both methods and we're going to talk about both methods and how they work. So this is, I will say, an unusual case. Typically we're not given a diagonal distance. Typically we're given a diagonal force and we use we can calculate the perpendicular distance to a diagonal force. It's very, very rare that we're given a vertical force and then a diagonal measurement. That's unusual. But still valid, and we're going to look at it. So that's a bit of an introduction to what we're going to do. So the first question, the wheelbarrow, is much, much easier. The first question, the lawnmower, is much, much easier. The second question, the wheelbarrow, is more difficult, and we will look at how to solve that. So what we're given here, this is called a space diagram. The space diagram, we draw a little picture. We could maybe show some ants, crawling on the wheelbarrow, whatever we want. That's a space diagram. Generally, though, we don't want space diagrams. What we want to do is we want to convert that instead to a free body diagram. And a free body diagram represents the same object. The free body diagram represents the same object, but it just converts everything into forces and members. Now, what I'm showing here, that's actually on a roller. But this is the structure that we're looking at. I'm going to draw this as a roller, but effectively this is the fulcrum that we're drawing. I'm just thinking that's going to confuse you, so I'm just going to say for the moment that we're going to take out the fact that it's fulcrum, and what we're going to do, we'll learn a bit more about pins and rollers later, but for the moment that doesn't matter. So what our forces are, I'll use red for forces. We have the known force, what do we know? We know the mass of the object. Now, because of transmissibility of forces, it doesn't matter if we draw our force for our weight. Now, I don't usually like to write W, I like to instead write mg. Mg could be written up here, or it could be written down here. It makes no difference to our calculation. The transmissibility of forces means it doesn't matter if it's written here or here. The same with F. It doesn't matter if it's written above or below. I'm going to write it in the same spot as the diagram for F, and I'm going to write mg above just to show you that it doesn't really make any difference where these things are written. Now, they've told us the centre of gravity, or the centre of mass of our object, and we know that the weight of the object can be imagined to be based at that location. So even though there's obviously mass of the object here, and there's mass of the object here, if we're told the centre of gravity, we can just apply the mass at that location, and the weight of the object at that location. So then we're going to have some distances, that's another part, and we have another force. The force is the reaction at the wheels. This is what's stopping. Obviously, if we have two forces down, the third force that's unknown, there must be a force holding this lawnmower up. Otherwise, it'd be getting crushed into the centre of the earth. So there has to be some point in which the lawnmower is being supported. So we're saying that it's being supported by a reaction force. And the reason why it's a reaction force is because that force can increase up to a certain limit. So if we added more and more weight onto this lawnmower, if someone stood on it and we started putting some elephants on there, the reaction force would have to increase up until a point where it can't produce that reaction force anymore. What we'd call that is the allowable bearing pressure of the soil. We don't need to worry about that so much. The idea is, when we talk about a reaction force can be anything from 0 up to the limit of that material. So in the case soil has a limit. So it's a reaction force, and so we're going to write that as R, and I might write RW just to say it's the reaction at the wheel. I might, because we know that if, in this case here, find the force to raise the front wheels. What they're saying is if we pull down on this handle, we're going to lift this up here. So effectively, the front wheel, if I said R for front wheel, and so in this case I could call this RW, but I'm going to call it R. we're going to say, well, at the moment that that's 0, we're going to lift this until the point where this reaction, the force on this wheel is 0. That's the moment, the exact moment where, the exact instant where there's no force on this wheel, that's what we're going to find. If we allowed the thing to rest, we'd have a different calculation, but they've told us effectively that this front wheel is going to equal 0. So if there's no force there, we don't need to write reaction that the front wheel equals 0. We can just remove it from our equation because it's not going to help us to solve this at all. So we've got 3 forces. We know that 3 forces in equilibrium must be either parallel or concurrent. These are parallel, so there's no point of concurrency. We can't use the 3-force method to solve this. So what I'm going to do is I'm just going to put some distances on here. Now, in Australian standards, we always write numbers above the line or to the left of the line. So I've got in millimeters 1056. Really, Copeland shouldn't have written millimeters there because it should be assumed that that's millimeters. In the case where we don't have enough space to write the dimension, we can write the dimension to the side. And so we're allowed to do that. That's what's going on there. Okay, so once we have that diagram drawn, well, so then what we have 2 unknowns. So even if we can replace mg and say, well, mg, mass times gravity of this object is 17 times the gravity of Earth, right? So mg equals 17 times the gravity of Earth. What's the gravity of Earth? 10 is acceptable. Technically it's 9.8, but for the sake of our maths, we want to make our maths easy, so we're going to make it 10. So it's actually 9.8. But we're allowed to use 10. Okay, so now that we have the 3 forces, the problem is we have 2 unknowns. So where we'd like to use some of the forces vertically, or more accurately, some of the forces in the y direction to solve this, we'd say, well, if we have 170 down, we're going to have some amount of, and then we have some amount of F. So we have mg, we have F, and then we obviously have a reaction force that has to be up, pushing up. The problem is we have 2 unknowns. We don't know what R is, and we don't know what F is. All we know is what mg is, which is 170. So, and to be honest, in this question, they're not even asking us to find RW, but I like it to point out that RW even exists, because I think that's important for your deeper understanding of how to solve these things later. Normally when we just say it's effectively a lever, right, we just compare the 2 distances, it's pretty easy. But I want to try and go into a little bit more detail and explain what's going on here. So we have 2 unknowns, and this is where the value of the sum of the moments method is so useful, is because if we measure all of our distances from this point, the rear wheel, then we multiply this by 0. And when we multiply anything by 0, it becomes 0 in our equation, which means we don't need to know what this unknown is. It gets eliminated from our equation. So what I'm going to write now is I'm going to write sum of the moments measured from W equals 0. This point here, I'm calling W. Okay, so I'm saying 0 equals, and I've got 3 forces. I've got F, and F is a distance of 1056 millimeters away. Now the question I have to ask is that going clockwise or anti-clockwise relative to W? So I like to think of putting my finger on W and I spin the wheel. Or you can think of it as a clock. I've got 2 arms of the clock. This is the minute hand. And if you push down the minute hand, is that going to turn this minute hand clockwise or anti-clockwise? Anti-clockwise. I like to think it's always important to put my finger on the location of the center of the arms of the clock. Okay. Da-da-da. Da-da. Da-da-da-da-da-da-da-da-da. Okay, so I've heard the audience yell out it's anti-clockwise. So I'm going to write here 0 equals minus F. Now the reason why it's minus F is because we've established clockwise as positive. I've said in other videos that in the past I used to use anti-clockwise as positive sometimes. I don't really do that. As a teacher, I decided I was always going to use clockwise as positive. You are free to not do that. Sometimes you'll see HSC answers that don't use that. Students, when I've marked students outside of the school, I've marked their work and I've seen plenty of people who use anti-clockwise as positive. At university and professionally, I personally used anti-clockwise as positive. I just like to be consistent, so that's where you know where this minus symbol comes from, because they've told us the arrow is going down. They've shown us on the drawing. Okay, the next force here is RW. Now, a lot of people wouldn't even write this in the equation, right? Most people would ignore this. And I'm just going to say RW multiplied by 0 equals 0. Most people wouldn't write that at all, because you won't see that in many textbooks, but I think it's important to acknowledge that that force is there. And the reason why we're using the moment method, the reason why we're measuring from the point W, is so that we can eliminate that unknown. And then we have a third force. We have mg, and mg is, we're going to assume that gravity acts downwards, it acts towards the center of the Earth. In this diagram, it's a pretty reasonable assumption it's going to be going down. So if it's going down, we put our finger on the center of the clock hand, and we turn. Da-da-da, 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 da-da-da. Okay, so that is turning clockwise. So I'm going to write mg, but I don't really need to write mg because I already know that value is 170. And then the distance is 220 millimeters. Now I can add those things together and I can put together an equation. So what I'm going to say is 0 equals minus 1056F. I don't even need to write plus 0, but just this once I will, plus 0. Okay, do you know what this calculation is? So did you do that? 720 times 220? Like 33 maybe?
Wait, 1720 times 220.
Close. 3740. Okay, so, and that's a positive. What we can now do is we can get this f and eliminate it from our equation, where we want to move it over to this side of the equation. So what we're going to do is we're going to set at both sides minus 1056f minus 1056f. They will cancel out. So we can rewrite our equation as f equals, sorry, we have to write it as, oh, we don't minus it, we add both sides. That's how these cancel out. Okay, so we have 1056f equals 37400, and then what we can do is we can divide both sides by 1056. Divide both sides by 1056. These will cancel out. So we can then write f equals 37400 divided by 1056. F equals, divided by 1056 equals 35.4 newtons. Now, keep in mind, we said originally it was down, so we need to include that and say that was the force down. Now, if we wanted to find R, we could use some of the forces vertically that we saw here, and we could say, well, 35 there, so this is going to be 100 and 205. The reaction force is 205 up. But they didn't ask for that in the question. They didn't ask for that, so we don't need to worry about it. But it's something they might ask. So in terms of kilograms of force, if you put a 3.5 litres of milk, right? So maybe if you bought a 4 litre, can you buy 4 litre milk? I don't think you can in Australia. It's the big square one you see in like Juneau. She's drinking 4 litres of Sunny D. Anyway, you buy a 3 litre container of milk, that would be not enough to lift up this, but just to give you a rough, I like to conceptualize what 35 newtons looks like. Okay, so we've solved that first question. I haven't checked the answer, but I'm confident of that. Okay. The next question is a bit more complicated. So what I'm going to do is I'm going to draw the free body diagram. The free body diagram of this looks like this. I know that I'm going to have I effectively can draw it as one beam, and I'm going to have a vertical force up, which will be the reaction. I know that it's going to be vertical because the other two forces are vertical. And I know that if there's 3 forces in equilibrium, that they must be either all concurrent or all parallel. So I'm deliberately writing this force below the line just to talk about that transmissibility of forces again, just to really reinforce that with an example. Okay, so we know there's a force, but what we don't know is we don't know the distance. We don't know the distance. We're given something that's close to the distance. I'll show you what we do know. We know this distance here. We're told that this distance here is 400. But this distance here we haven't been given. What we're being told instead is a diagonal that's not the perpendicular distance for this force. We've been told this is 1215. And with that force, well, we have either two choices. What we can do is we can keep the perpendicular distance that they've given us, and we can convert F into two forces. So we can set up our own, we can break it down into components and use the forces. We're going to start with that method. The second method, what we're going to do is we're going to replace this blue distance. We're going to replace it, we're going to calculate what the perpendicular distance is instead, and that will look like this. That's what a perpendicular distance looks like. And the idea there is that this force continues down, that's a perpendicular angle. Now it's really important because that's our formula, moments equal force times perpendicular distance. If I had $1 for every time a student didn't convert things to perpendicular distances, I would have a lot of dollars. Okay, so what we're going to do is we're going to replace F, and we're going to replace F with two forces that we're going to break F in, which is we're going to break F into, currently it's a vertical force, but what we're going to do is instead, we're going to break it into two forces. We're going to break it into a force like this. We're going to say that partly going up that way and partly going up that way. That's our F. We're going to call this one here Fx and this one here Fy. That's what we're going to call that. Now, so I'm going to write those forces in here. What they'll look like here is this will be Fy and Fx will go there. Now, to break that force, we're just using trigonometry. So if we're told that this is 15 degrees, well, the short version is that if this angle here we're told is 15 degrees. We're told that's 15 degrees. So if we add 90 degrees there, this will also be 15 degrees. If that there is 90 degrees. Does that make sense? Okay, so let's do that again, because I can see a puzzled look. 15 degrees, what's this value?
85?
85, that would be too much.
75.
75. Okay, 75. And then, if I got rid of that, and I said, okay, now I want to know the perpendicular force there, what's this one?
15.
15. Okay, so a lot of the time I'll just rush through that. And I just trust that you have the geometry, but occasionally, for the first or second time that we show these things, I'll draw it and prove that the angle is in fact 15. Okay, so what we've got here is we've got F, and what we want to do is we want to take a 15-degree version of that, and we're going to break it into a right-angle triangle. A right-angle triangle that's 15 degrees. So F, find the force required to lift the wheelbarrow of the total mass. Okay, so we don't know what F is yet. That's the problem, right? F is a question mark. And that's what makes this more difficult. Now, we have been told mg. Mg equals mass times gravity, which is equal to 24 brackets 10, which is equal to 240. Remembering, of course, that it's not really 10, it's 9.8. But we're allowed that 2 degrees, that 2% error. We're allowed just to ignore that in engineering. In physics and in real life, like once you're getting paid for stuff, they expect you to use the calculator. But for us, it's just simpler to use 240, and where possible, we're going to try and simplify things. Okay. So, what does our equation look like? Well, how many forces are there on our diagram?
3.
Okay, there's 3, but we've broken F into 2. Yeah, so we could say there's R. The R is the reaction at the wheel. And again, we're going to call this point W for wheel. That's this point here is W. So we have the reaction at the wheel, that's 1. We have the weight, mg, and we have the 2 Fs. That's what we've got. So what's our equation going to look like? I had a black marker and I don't know where I put it. It rolled away. Don't worry guys, I got it. Okay, so what we're going to say here is we're going to say that the sum. Well, okay, first of all we're going to set clockwise as positive. I already talked about that enough for this. And then we're going to say the sum of all the moments measured from point W. Now I could take this from literally any point, but the thing is I've got 2 unknowns. Well, actually I've got 3 unknowns. I have these Fs and I have this RW. And the thing is, that's just too much going on. So what we're going to do is we're deliberately going to choose a location that includes one of the unknowns. And RW is one of the unknowns. So we're going to take RW, so that way the perpendicular distance will be 0. Okay, so that distance equals 0. That's our starting equation. So once we know that, what are we going to say now? Well, what's our first force? RW. I'm going to write minus RW because it's a lot easier to turn a minus into a plus. So I don't know if it's going to be clockwise or anti-clockwise yet. Well, I do, but you know, I want to keep the suspense. So I have this force RW, and relative to the point W, is it turning the beam clockwise or anti-clockwise? Ooh, I'm confused.
No, which force are we talking about?
RW.
Anti-clockwise.
Anti-clockwise. So you're saying it's turning the beam that way. How far is it? What's its distance?
Well, it's 0. So
it's 0, so it's not clockwise or anti-clockwise. I tricked you.
I mean, I have that written down on my sheet.
Ah, okay, good job. I didn't trick you. You were too smart. Okay, so what I'm going to do is I'm going to put this in blue just to say you don't need to write that. Yeah, the blue stuff there is just like a bonus. Okay, so then the next force is mg. Now mg we've said is 240 newtons, and the distance to that is, I'm going to use meters, even though I like millimeters. I just don't like writing all the zeros, so I'm going to write 0.4, and I'm willing to bet that's what Copeland wrote in his answers. Okay, so 0.4, and then I've got fx and fy. Okay, so then I've got fx, I'm writing minus fx. Okay, smart kid. What's the perpendicular distance to fx? 0. So it's neither clockwise nor anti-clockwise, yeah? So fx we can effectively ignore, right, for our equation. And then we have fy. I'm writing minus fy because I don't know if it's clockwise or positive, well, not yet. So if I put my finger on W and I push that arm, is it turning clockwise or anti-clockwise? Anti-clockwise. So it's going to stay as a negative 1.15. Okay, so let's see what we're going to look at. Straight away, for the first time in a long time, I'm just going to bring this straight over here, and I'm going to assume you can follow the algebra because I literally just did it a second ago. This is going to multiply, and then because it's a minus sign, I can bring it over here. So I'm going to say 1.15 Fy equals, can you tell me what that number is? Like 100? I think it might actually be 100, but, oh no, it won't be close, 98 something. 96. Now, I didn't put that plus there. I should have. Be really careful when you know, it's hard because I spent a long time talking, that it's definitely clockwise, right? Weight is definitely going clockwise, so I need to make sure my symbol is positive. Okay, so if I know that that's 94, well that means Fy equals 96 divided by 1.215 equals Fy equals 79 newtons. And that's going to be going like that. The problem is, that's not F. They asked us to find F, and we've only found a component of F. So what we need to say now is that if we know this value, if we know this equals 79, right, then what is F going to equal? Okay, to do that, we're going to need some trigonometry. So what do we know? We know, well, okay, I'm going to write out the famous phrase, so, ka, toa. We know, what's this? Is this the angle? This is the angle here. Is that adjacent or is it opposite? This big one here is the hypotenuse. We know that that's the definition because this is 90 degrees and that's opposite.
It's still adjacent.
It's adjacent, yeah. So it's going to be that. That's the letters we have. We know the adjacent and we want to find the hypotenuse. So what we can write here is that cos theta equals adjacent over hypotenuse. So if we want to find hypotenuse, we reverse that. Hypotenuse equals adjacent over cos theta. So in our case, what we can write is that F is equal to 79 divided by cos 15 degrees. 79 divided by cos 15 degrees equals F equals 81.8. And that's straight up. That's how you would find that answer. That is I like the idea of lever questions for the preliminary mid-course review, the test that I do at the end of term 1 for year 11. I like these questions, but I think this one's too easy and this one's too hard. But if you can do both of these, you're probably going to have a good chance of doing well in that exam. So we've got those two equations, those answers, but I said as a bonus that I was going to solve this using this method here, the perpendicular distance method. So let's have a look at that. We have an answer in mind that we know what we want our answer to be. We want our answer to be 79 newtons. But we're not going to use this method. We're going to instead find this blue value. Okay, so now I want to remind everyone that this here is a perpendicular angle. This distance here, if I extend the force down until it's where it's closest, this is perpendicular. So there's lots of different ways of doing this. What I sometimes say is, I want you to draw the force, in this case force F, and I want you to extend that line all the way up and down, and then I take a set square or even just a piece of paper, and I will just lower it down the line until it touches W. And so that's where it's perpendicular. And then I just want to measure that distance. Now, what is really interesting is if the drawing, if the drawing doesn't say not to scale, you are allowed to measure off the drawing. If the drawing does not say not to scale, and even if it did, if you did it in my test, if you did, even if it did say not to scale, I would say if you were really freaking out, you didn't know what else to do, I would say you could do a lot worse than measuring things to scale. You'll at least get some marks. You know, the marker could be feeling really generous. Okay, so what we want to do is we want to find this perpendicular distance. Now this is going to use some trigonometry, but the other way you use trigonometry, and for me, I felt that the other way was a little bit more complicated. There are pros and cons to using both methods. There are definitely times where I want to use both methods. But what I'm going to do is I'm going to go over here and say if I have this distance here, and what they've told us is this long line here is 1215. And we know this angle is 15 degrees. So what we want to do is we want to find which side is this?
Adjacent.
Adjacent. So we're going to use cos. And so what we know is that cos theta equals adjacent over hypotenuse. So if what we want to find is the adjacent, what we can do is we can write this here as going to be equal to the hypotenuse cos 15. So that's what our side is going to be. So if our hypotenuse equals 215. Then our distance here, what is our distance? 215 cos 15 equals... Now, this is where a good place for some estimation. I have estimated that this number has to be smaller than the hypotenuse. Yeah, it has to be smaller. So when I write down here 1173, I feel good about that value because it is indeed smaller than the hypotenuse. So what I can now write is here f, and f is still going wait? F is going up. I drew the wrong way. Good thing I looked at the drawing. Okay, F is still going anti-clockwise. I'm going to convert this into meters. I'm just showing you where that number came from, that's why I'm keeping it in blue. So what I can say now is I can say minus 1.173F equals, we've already done 240 times that, we said it was 96, I'm pretty sure. But you know what, I'll type it in just again. Divided by, well, if I divide both sides by I know F, no line, that disappears. F equals 96 divided by 1.73. 96 divided by 1.173 equals 81.8. 81 is what our answer is, and that's what we got last time, so we've proved it right. And I just had a question from a student asking, why would anyone use the first method? Why wouldn't this just seem so much more apparent? It's really, the question is trying to push you in this direction. It's giving you this angle, and it's, I think the way that they've shown that angle is to try and push you towards using perpendicular distance method. Me personally, I really like the perpendicular distance method. I don't see that method used very often, and I think it's a much better solution. What we tend to see is we tend to see people use that first method, which is to break the force up into components. Now, there is a really good reason at times to break things into components, and that is so if you've got all your forces in the same direction, so I've said here x and y, if you convert all of your forces into horizontal and vertical components, it's often much easier for you to find answers at the end. Yeah? So that's why it's beneficial. This, I find the perpendicular distance method is a very fast and effective method. It's especially valuable because a lot of the time, if the drawing is drawn to scale, if the diagram is drawn to scale, which we can usually assume it is, even in the 2019 HSC, there was a question that said not to scale. Now, I can't say in a recording that the HSC markers ignored that not to scale, but I would feel confident that you can reliably go into an exam and see if you have a truss question, if you have a beam question, you have to find reactions. If you take that perpendicular distance and just measure with a ruler and just draw it to scale, there's a good chance that you're going to, if you don't get it right, get a lot of marks towards the working out. Especially if you have no idea what to do. You can just set your set square, find the perpendicular distance, and off you go. Whereas the alternate method of converting everything, usually what we want to do is we want to convert things to horizontals and verticals, which is why this is such a bad question, because to solve this, we have to convert it to something other than horizontals and verticals. What we're doing here is we're converting this force into something that is in the same line as the dimension they've given us. So they've given us a dimension, and we're taking this force F and we're converting it into something that lines up with the dimensions they've given us. Now, most people will look at this and say, well, it's easier to change the dimension than it is to change the force. But it's important to remember that, no, often we want to have all of our forces be in the same horizontal and vertical directions. And so that's why it's often better just to start off with, and Copeland recommends in his textbook, that when you're solving beams, you should actually start from the premise of just convert everything into horizontal and vertical components, and then work out your forces from there. Now, I personally think I'm a much bigger advocate for the diagonal method, the perpendicular method, than most teachers, but I think there's a place for both. And especially a lot of the time you're going to have to break this thing into vertical and horizontal components to solve it anyway. So I can understand Copeland's reasoning to say that in his 5 steps to find reactions, step one is do a free body diagram, step 2 is to break it into horizontal and vertical components. Does that make more sense? Yeah. I appreciate there's going to be one that stands out to you when you solve these questions, and that's never going to be wrong. I think the perpendicular distance has a real advantage, which is that because, given that HSC questions are effectively always, and if not always, almost always, drawn to scale, if you're having problems, this is a way to bypass that problem. It's kind of like a cheat code. But there are some advantages to, and there's a reason why breaking it up into forces is the default method. So we just go, I'll do a quick revision. So these are the 3 rules that we use to solve all of our questions. When we have 2 unknowns, we solve it using this formula here. The sum of the moments equals 0. That's true if it's in equilibrium. That's true for literally every location in the on the beam or the system. Now, what we need to know is that moments equal force times perpendicular distances. The perpendicular distance part is what catches out a lot of people's problems. What we saw here is this question is really easy because they've given us forces and perpendicular distances. That's a little too easy for an exam, maybe for 1-mark question in the first couple of multiple choice. But if I'm going to make you solve something, I'm going to make something a bit more complicated than that. I'm going to test your knowledge. This question here, I find a little bit more difficult than what we'd normally give you. I would be much more inclined to give you an angled force, but give you the square distance. But when we do have something like this, what we have is 2 options. We can either do the first thing which we saw, which was to break F into components, or the second thing, which is to find the perpendicular distances.